Okay, let's have a closer look at the hard constraint. And to do that, I'm going to drop down a geometry. I'm going to delete this, and I'm going to drop down a sphere. And I'm going to make this a polygon. And put this to 3, put down a transform, so I can move it up a little bit. Something like this. I'm going to use a Voronoi to fracture it. Like so. And I'm going to drop down a scatter. So I have some fracture points here, and I'm going to put this to 30. And I'm going to visualize the pieces so you can see them. So here are the pieces. Cool. So the next thing we need to do is to make this to packed primitives. So I'm going to use assemble. And in here you have this create packed geometry. So in this way, now every piece is a packed primitive. Now we need some polylines for the constraints. So I'll use connect adjacent pieces that will create polylines between the different pieces. And here I'm going to use connection type, adjacent pieces from points, perfect. We don't see anything though, it's just because the search radius is too small. So let's get up that a little bit, 3 as max connections. So here we have some polylines that connects our pieces. And before, the 2 points on each polyline was the same place, so the rest length was 0. But in this case, I want to use the actual length. So I'm going to set this, and then it's going to save the actual length as a rest length. Cool. Okay, so let's drop down a DOP network. So the DOP network is here. I'm going to connect these guys in here. We're going to have a rigid body solver. I'm going to put in here. We need a packed primitive. So everybody packed object. And in here, let's take the geometry source, point to the first context geometry. And the first context geometry is this one guy here. So in this way, now we have this guy in here. And what do we else need? We need some gravity so it can't fall. We also need it to collide with something, so I'm gonna drop down a ground plane. So the ground plane is here, and then I'm gonna drop down a merge. And here is the merge, and in with the ground plane. And I want it to the left, because left inputs affects the right inputs. So now we have a simulation at least. But it's just breaking apart, not really what we want. And so we need to create the constraints as well. So let's drop down a constraint network. Here, oops. Here is that, and in here, geometry source, let's do the second context geometry, which is this one here, where the different polylines comes in. So the next thing we need to do is we need our hard constraint. So let's do a hard constraint, connect it in here, and let's name it pin as before. But currently our polylines doesn't have any constraint name because we haven't specified that yet. So now it doesn't know what to look for, so if we would play this, it will still doesn't work, and we could get this error because there are no constraints. So let's go and define these names. So we're going to drop down a wrangle here, and we also make sure we want the name on the primitive and not on the point. So let's change this to primitive, do s as in string, attribute s at constraint name, and we want this to be pin. Alright, so this should work. If we go back here now and try it. Ah, perfect. We can see that this sphere is holding together by the constraints. So the first thing we can see that there are 2 constraint types with hard constraints. So if I'm gonna put some velocity on this, and then you can see the default constraint type is just the positions. So it doesn't try to constrain it by the rotation. So if I put this to -20, and boom, you will see it a bit wonky, because it's only constraining the position, not the rotation. If I would change this, you can just specify that the constraint type as rotation, but I want both positions and rotation, so I'm gonna do another attribute here as constraint type, and I want this to be all. So now if we do the same thing, is a little bit better. Cool. Let's continue. What else can we do here? If we said, I'm gonna set this more to -10, so it's not as crazy. If we look at the hard constraint, we have these 2 things. We have the rest length. So the rest length here is 1. Before it was 0 because the anchor point was at the same position. But in this case it isn't, and we have set the rest length in an attribute. That value will be multiplied with this value. We also have the constraint force mixing and the error reduction parameter. And the error reduction parameter is how much, if the constraint gets violated, is how fast it will try to correct that error. So if we would put this to 0, it do no correction. So then it will just sliding apart because it doesn't try to correct it. If we do it really extreme, put it to 1, and now it tries to do all corrections on the same frame, which results in a lot of crazy forces and makes it very unstable. So the recommended values are between 0.2 and 0.8. So let's put 0.2 again. And constraint force mixing it tells that the constraints can be violated if the force is strong enough. So if I would put this to 1, now the force was enough to get them violated. And even if I would put this error reduction to 1, it will still get violated just because of this constraint force mixing.